Hello, welcome to chapter 20. We're going to look at processing units now. But before this, you would probably have already watched the video and you know that there are so many different types of sensing device and they kind of operate like switches. Like for example, the LDR is triggered by light, thermistor is triggered by a certain temperature that you can set by adjusting your potential divider circuit. If you have no idea how these things work, I highly recommend you pause the video. I'll still be here. Go and watch the chapter 19 video first. In this entire chapter, we are going to look at the processing unit, or like what I like to call the brains of this flowchart. So if let's say you do some basic biology or in your sciences, the sensing device are like your five senses. You can see, you can hear, you can taste, okay? And then it goes into your brains, and your brains go like, this is a new information. What do I do? For example, you put your hand on a boiling kettle. Your brain will immediately trigger an output that always sends a signal to your muscles. So your muscle will respond. And of course, this process is very fast. If not, then, something bad will happen. But we want to be able to actually use circuit because technically your whole body is a big circuit, right? Your body's cell communicate with each other using electric impulses. So here, this is also like a big circuit, and we want to be able to use computers to help us make decisions so that our brain can chill a bit and study physics. So the processing units that you have learned before, whether you know it or not, are the logic gates. Your AND gate, your OR gate, your NAND gates, okay? So this is in the past. We will leave this behind. Our focus is the operational amplifier. And this entire chapter will be devoted to the op-amp, fondly known as op-amp because physics people like short form. This is our main focus, okay? And you may be thinking, what are our output devices? You will find out somewhere along the journey of the chapter. But let us first understand what is an op-amp and how does it look like? And why is this so important and pivotal in the operations of computing or computers? So you see behind me is a picture of how computers used to look like in the 1950s and 60s. And I think you've probably heard of stories before about computers being really, really big. They take up the size of an entire room because you see all these circuit components, right? They need to fit somewhere and they need to be certain spacing between them and some cooling system so that the whole thing doesn't overheat. And you can see these people, they are trying to read the code that is generated from the computer. All right. So right now, obviously, computers don't look like this right now. At least I hope that you're not watching the lecture from a computer that looks like this. All right. So how did we manage to make something that is so big to something that is so small that can fit into your pocket? Because if you think about it, generally, when we design a prototype, your circuit will look like this. There are many wires connecting here and there. You're stuffing everything into a box. But after a while, if let's say this circuit, the prototype works, we will begin to print out 3D printing or just regular printing circuit boards with designated connector. There are actually two op-amps here and maybe some electrical component that look a bit familiar to you. Like for example, I think this looks like capacitors. See, all these are capacitors from your chapter 18, right? All these things here, this one, the turn, all have knobs to turn. These are potentiometers. Okay, or your potential dividers. You can see all of these tiny things. These are all your resistors. They look very neat, not like any of the circuit that you have connected in your AS paper 3 because it's a designated, printed, organized circuit board. Whereas compared to this one, this will look like what you build in the lab. So if it works, we will then manufacture it this way. Okay, and where is our main star in this topic? Op-amp is this tool. This is the brains, the op-amp. Okay, the op-amp is here. And of course, we also have a bunch of resistors and capacitors and different type of components. So if you study electronics engineering or if you do some physics that require you to design some circuit boards, this is roughly where what you'll be dealing with. But you're like, Miss, I don't think my phone can fit this one inside. If you're thinking about that, you're right, because your phone's circuit board look like this. Cool, right? It's so small, it's so tiny, it's so thin. And the only way to actually observe the circuit is actually under a microscope. And because we managed to make circuits so thin, we are actually at the limit of how small things can be. Your phone can't be thinner. Your computer is already at the smallest possible size. But before we talk about how it gets so thin in the first place, we need to rewind and understand the very beginnings of basic computing. The very, very first step, which is the operational amplifier, right? So you might be thinking, this operational amplifier looks like a black circuit component, but what is inside this black circuit component? Well, my friends, I'm glad you asked. I will show you how it looks like on the inside of the black box. So we now look under the so it looks like this inside that little tiny black color circuit component. Okay, and you might be thinking, okay, I recognize some stuff. Like for example, oh, we know this is the symbol for resistor, although in your syllabus we tend to draw resistor in a different symbol, but these are all resistors. You can recognize the unit, you can recognize a few capacitor, but what is this fan shaped thing with the three legs? These are all what we know is known as transistors. But transistors is not in your syllabus unless you did Form 5 or the Malaysian Form 5, which is SPM, or any kind of IGCSE equivalent that talks about transistors as a circuit component. So if you don't know, you can just understand that the transistors have a few very basic properties whereby it operates like a switch. It can turn on, it can turn off. Or in computing language, it can be 1, which is turned on, and 0, which is turned off. We will look more into ones and zeros when you study chapter 16, communication, later somewhere in your future. Okay? And transistors are very sensitive things because they consist of semiconductors. And we don't want to spoil or overload the semiconductor. So we prefer to have small current. Okay, small current to prevent overheating. These two will allow you to understand why, when we talk about the properties of operational amplifier, why they have certain properties and why not. But if you're really interested in like why are they coded different color, how does this one work? Well, guess you have to do a bit digging, okay? Or maybe if we can afford it, we'll record another further physics video. So now we're going to move on to what exactly does A-level require of you? How does it look like on paper, and what are the important things that you need to know. Just bear in mind that in the big picture, this is the very beginning of modern computing as we know it. So let's go. So this is how your op-amp looks like, right? The general op-amp that we will use have the 741 code, okay? And you can see that it has 4 legs on each side. 4 legs, 4 connectors. You can connect this normally to a chipboard, all right? Not through your crocodile clamps anymore because we have level up, all right? But these are the connections. And of course, this one looks a bit confusing, right? Because you have certain pin that you don't use, okay? And certain pins are just there to restart the op-amp, which we call that offset null. The important connections are actually the other ones, which I will highlight now for you. The input, so these two are the input, okay? And then we have the output. Of course, what goes in must come out. That's the universal law. So the output is here. And we have supply voltage. These two are your supply. So if we keep drawing like this, it will actually confuse people. And your supply voltage actually have a positive and negative power source, right? So when we move it up to a circuit component, it is labeled this way. So let's label them together so that we are not confused, okay? So we label them together so that when we see the numbers, because sometimes in the paper, they may not be so nice as to label to you what it means. So at least you know how to name the important 5 input, okay? So generally, right, if you think about reading, if you follow language like English, we read from left to right. So whenever we draw a circuit component, we will visualize input from the left and output to the right. So the input is the 2 prongs at the side. You see this minus, you see this plus. These are the inverting and non-inverting. So why do we use the term inverting? This one will have to wait for later when you learn about negative feedback. But right now, I'm going to draw the ground level. Okay, so whenever we look at circuit like this, sometimes we don't even bother to draw the power supply anymore. Because The power supply is assumed to be there. And we will just draw the ground level because the ground level is our reference point, right? So your minus, this minus is inverting. So whatever you apply to this connector here, the potential from here to here, okay, is known as the inverting input. Symbol that we will use is V minus. Sometimes they put the minus on top. Okay, and for the other one, plus. So you don't invert, non-inverting. Okay, here to here, non-inverting input, this is V plus. So these are both of your inputs. We will measure from ground level. So basically, whatever potential you input in plus and minus, inverting and non-inverting, will decide what the output will be. And when looking at this, right, it's also important to understand that there are certain years where they will flip and they will draw the plus on top and the minus below, and certain years they will draw the minus on top and the plus below. It's very important for you to just, when you see a op-amp circuit, take a breath and you're like, you can't trick me, and you label all the input, okay? And this is the output, right? So again, from left to right, so this is the output. And the output, again, is measured from ground level, okay? Because ground is our 0 volt, 0 volt. Okay, it's like your x-axis for your graph. Whenever you want to read a value from the x-axis, you read from 0, right? So this would be the output. Just going to call this V out. All right, and you see these two whiskers here. Whiskers. I like to call these whiskers, but they are actually your power supply. Okay, so whiskers. So this one is the positive V supply. Okay, and this would be negative V supply. It's the supply voltage to give power to the operational amplifier. Okay, you might be thinking, also voltage leh. Why can't this input give power? Okay, one by one. The input is to tell the op-amp how to behave. Turn on, turn off. Okay, the output is what happens because of the input. Supply is just there to make sure that the op-amp is running. Okay, so it's a bit like right now I'm talking to you and my words are the input. The supply is the fact that you have eaten your dinner, your lunch, your supper, and you are okay lah, you're happy. You are currently being supplied by calories. Okay, and your output will hopefully be past year questions or certain knowledge boost in physics. So although these are all V, and if let's say for example you're still not yet used to the idea of circuits, right? It's important to just take a while and ask yourself, what are the difference between all these V's? One is input, us telling the op-amp to think. So for example, right now, if let's say you look at your computer, when you type something into your computer, what your keystrokes, every single key that you press is an input. Your computer is connected to a power supply all the time. If not, a computer cannot run. What is the output? Means the alphabet appearing on your screen. No? Let's say you type ABCD, then the ABCD will appear on your Microsoft Words. So these are all electrical signals. When you press your key, the electric signal from your keyboard will send to your processor inside your computer, and will send another signal to tell Microsoft Words to display the alphabet to you. Of course, you won't think of it this way because it happens with almost no lag, which is, by the way, one of the properties of the ideal op-amp. But your computer has to be connected to an external power supply that is not dependent on whether you press or you don't press your keyboard. If not, that will be a bit stressful. All right. So with that in mind, let us think about what are the properties of an ideal operational amplifier or ideal computer. All right, so let's look at the properties of an ideal operational amplifier. And here you will see a lot of words like I never see before. For example, what on earth is impedance? What on earth is open loop gain? What is bandwidth? What is slew rate? Okay, so before you panic, please don't panic. These kind of things are like facts that I guess you could memorize, but it'll be easier for you to memorize if you understand what they mean. And as you study the types of operational amplifier circuit that is included in your syllabus, you can always revisit this part and go like, oh yeah, it makes sense now. Okay, so right now it's just an introduction to you, and also because you know how like paper 4 they always like to part A ask you to define something, but now they can't really ask you to define anything. So what they'll do is they'll ask you to state 3 properties of ideal op-amp, or explain what is meant by infinite input impedance, etc., etc. So it'll be good if you briefly know what it means, okay, and operate from there lah. So let's talk about impedance first. What is impedance? So if you are pretty okay in the language called English, you will know that impede, am I spelling this right? Okay, so the word impede here generally means to delay or to slow. Vocab of the day. Consequence of being my students, you learn a bit of English. So when we say to slow, right, what are we slowing down? Generally, in a circuit, we slow down the rate of charge flow or the current. But in this case, right, this impedance, you can see this as the resistance. That means why they don't use resistance? This is resistance specifically for alternating current. This is because, right, your AC circuit is pretty cute. In a direct current circuit, the only thing that can slow down the charge flow is resistance, a resistor. But in the AC circuit, we can put other components to slow down the alternating current. For example, we can put a capacitor there. The capacitor will charge and discharge. Depending on how easy it is for the capacitor to charge and discharge, the current will flow differently. So this resistance for alternating circuit, I'm going to put a big inverted comma, because this resistance or this impedance actually depends on other circuit components, not just the resistor. Okay, so hopefully that would explain the term impedance to you. All right, but what is meant by zero input impedance? Input is the signal, right? And if we have a lot of impedance or resistance to the input signal, this means current cannot enter the op-amp. And we don't want current to enter the op-amp. You know why? Because the op-amp, if you remember, it consists of so many transistors. And I've mentioned before, the transistor don't like large current. It will burn, it will spoil, this thing will not work anymore. So the infinite input impedance is to prevent current from entering input, from entering the op-amp. Okay, so in the process of saving space, I will try to type that out. All right, so no current enters or leaves the input of the op-amp. So to make that happen, we will have infinite input impedance. But also there's a second reason why we want infinite input impedance. Okay, and we don't want current inside the op-amp, especially from the input part of the circuit. This is because if you think of what you have learned in your sensing devices, all your sensing devices will be connected to these two input of your operational amplifier. Okay, so if you're wondering how it looks like, I will discuss this example in a later video, but it looks kind of something like this, right? You can see there's a potential divider bridge here. I will highlight for you. Okay, where there's a 1.7 kilo ohm and there is a LDR here. Okay, so this is a potential divider circuit. And if let's say for some reason, this is not a very good op-amp and some current leaks into here, then the potential divider, the potential across these two components will not be the same anymore. And we kind of want to avoid that at all costs, right? You don't want your computer to be affected by itself. Okay, so whatever that you are input, it should be on its own, not affected by the op-amp. So this is probably the second reason where we can say that the presence of the op-amp should not affect the potential differences in the potential divider. Okay, so this is a very brief explanation about why we want infinite input impedance. But what about output impedance or output resistance? Again, in big inverted comma. Okay, we want zero output impedance because we also don't want this to steal any of the output potential. So this output potential is supposed to be sent to an output device. For example, it should be sent to, like, if you look at this diagram again, it could be sent to an LED. This LED is supposed to light up, and if let's say the op-amp went and took some of the output voltage, then the LED may not get enough voltage to light up, or it may not be as bright as it is intended to be. So the ideal brain is a brain that doesn't affect the output and doesn't affect the input, but it must have different properties, output and input. For the input, it should have infinite resistance. For the output, it should have zero resistance. But you cannot use the word resistance because this is not necessarily an alternating, not necessarily a direct current circuit. So you have to use the term impedance. Okay. Okay, so the second property, zero output impedance, because we want to prevent the op-amp from drawing or taking up any of the potential difference, any output voltage from the output devices. Okay, so the best brain is the kind of brain that doesn't disturb the input or the output. Cool? All right, so the third one is infinite open loop gain. Okay, there are a few terms here that we need to address, mainly open loop. What is open loop? And the word gain. Okay, so I think I will write out the equation for gain first. When you think about gain, right, if let's say you do maths, you can think about magnification or multiple. Gain, most often in your syllabus, the symbol that is used is capital G. It's defined as the ratio of output to input of your op-amp. So for example, if your gain is 2, it means that you input 1 volt, you output 2 volt. You input 10 volt, you output 20 volt. Now, how I wish I have this kind of gain with my money. I put in 10 ringgit, I get 20 ringgit. Then I no need to teach physics now. Can retire in a nice island. And this one is even nicer. It is not 2. The factor is not 2. It is infinite. Wow. This is ideal lah, okay? But Miss, what about the normal op-amp? They have properties that are very close to ideal. So it may not be infinity because no one knows what that is, but it's very, very large. Okay, so this is gain. But what about open loop? Okay, so when we say open loop, right, we are referring to the connection between the input and the output. Okay, so you think about feedback, or you think about, for example, a closed loop. So if let's say I again refer back to this circuit, this is the input. These two things is input. So this is V in, this is V in. And if you want to, this is actually the inverting input. This is the non-inverting input, right? And here is the output. V out. V out is not connected back into the input. So there's no feedback. So if there's a connection here, I take a wire and connect here, here to here. This one is what we call a closed loop. Okay, is closed loop in your syllabus? Yes, but right now we're focusing on the open loop first to not complicate things. So a feedback system would be, I teach you something, you go back and brain it in your processor brain, you do homework and output, and then I look at your homework, and based on how you do your homework, or you ask me questions during CC or AMAs, you go and ask your lecturer question, they will give you new input based on the question that you ask. And then you go and brain the new input, and you come up with new questions, and you ask your teacher. And this loop goes on and on, which is the best way to learn, by the way. But sometimes students, they don't ask questions. So the loop is not closed. So we're like, do you understand? You don't understand? Silence. So learn to give, ask questions, because there is a closed loop, which is great. But right now for the amplifier, or when you talk about properties, we are looking at the simplest connection possible. We are not going to close the loop yet. So that is the definition of open loop. Okay, so I'm going to type out the definition of open loop. Right, so this is what is meant by open loop. When there's no component or connection between the output and the input of the op-amp. So let me highlight this. Between output and input of your operational amplifier. Okay, but what is the implication of very large or infinite gain? This means you put in a little bit of input, you get maximum output or very large output. Okay, so this means for very small input or V in, the output is maximum. So this maximum output has a very specific term. We call it saturated. It's a bit like your brain is saturated sometimes. Full liao cannot be larger liao. And saturation is when the output is equal to the supply voltage. Let us revisit our drawing of this op-amp again. Now, I say that this supply is supposed to give energy for the op-amp to work. So the op-amp is going to pull the energy from the supply to create the output. Very much like your laptop is pulling energy from your PowerPoint to give you this bright, beautiful screen. The brightness of the screen cannot exceed the power that can be supplied by your PowerPoint, your plug point. Okay, so this supply voltage is the maximum amount of power, because remember, voltage is work done per unit charge. So any form of energy references or power references, we go back and look at the voltage. So this output, the largest this one can be, is the largest that the supply can provide. No larger than that. All right. So this means that when saturation, your output is equal to your supply voltage. And from the idea of conservation of energy, this output is either less than or equal to supply. Always. Okay, always the output is less than or at most equal to supply. And when it's equal to supply, we call this saturated. All right, because you can have infinite gain, but conservation of energy says that you are still bounded by how much we are putting into the op-amp. Right. The fourth property is infinite bandwidth. Now, you probably heard of this term bandwidth before. Like you go and say like, oh, I want a large bandwidth for my internet. But what is bandwidth? Okay, so this is what is meant by bandwidth. Bandwidth, you will see more of what is bandwidth in your chapter 16, communications. Okay, but bandwidth can, roughly speaking, be range of frequencies to be amplified. You might be thinking, what frequency is this? Is this sound wave frequency? Generally speaking, that is when the input signal is AC. You know, your alternating current has a certain frequency. So it is indiscriminate one. When we say infinite bandwidth, means it doesn't matter whether the frequency is very small or the frequency is very large, it will be amplified equally. So input signals of different frequencies or all frequencies will all have the same gain. You put a small frequency AC, maybe 2 Hertz, the gain would be the same. If let's say you put the same AC signal, but you increase the frequency. And the reason why this is important is because actually when you put in AC of too high frequency, the output will look a bit unstable. Because the AC is flipping too quickly for the amplifier to register the changes. Which brings us to the last one, which is called infinite slew rate, or what I like to say, no lag. No lag. Okay, so slew rate here is defined as the response time. Okay, I will type it up. Okay, as previously mentioned, slew rate is a measure of time delay. Okay, hang on. Measure of time delay. And this time delay is between the changes of the input to the output. So as you can see, right, my laptop recording this, the slew rate is not infinite. The time delay is very large. Because whenever I drag and pull something, the whole system will hang a bit. So you can observe that actually in the recording. You could even observe that between the sound that you hear and the movement of my mouth. So all of this is the time delay. And a perfect or an ideal op-amp or ideal computer will have no time delay, which is what we call infinite slew rate. All right, so whenever I change my voice or I say something different, I change the input to my mic, there's no time delay between that and the image registering on the webcam. So these are the properties of an ideal op-amp, which is generally how we want any form of circuit to work. We want the computer or the op-amp to not affect the input and not affect the output. So it does so by adjusting the impedance. We want it to have large gains and infinite bandwidth and infinite slew rate. So take some time to brain all these terms, and whenever you do an op-amp question, maybe after a while, whenever you finish a circuit, you can reflect on how these properties actually allows the circuit to function the way it's supposed to function. Okay, so this video is going to be quite content heavy, and it feels like, wow, there's a lot of definition to memorize. But the idea of telling you these properties early on rather than at the end of the chapter is so that, number one, when you do past year questions, you can use those past year questions as an exercise tool to recall these facts. And number two, this op-amp is supposed to operate like a computer. So you can always use the idea of, like, I want a computer to work. What kind of properties will allow the computer to function the best it could? And also when it comes to these kind of facts, which you will have more and more as we enter into the deeper application chapters of A2, learn to use skills like mind maps to memorize or flashcards. Okay. All right. So that's it for this video. In the next video, we will look at the very first circuit where we are going to install the op-amp in its entirety with the sensing devices and also with the output devices. All right. So that's all. If you find this helpful, please share this video with your friend. We'll learn physics together, and I will see you in the next one. Bye-bye.